This video explains the calculation of moment capacity for under reinforced rectangular sections of the beam. In the previous video, we looked at the strain distribution of the under reinforced section. So we are focusing on the calculation because it's a ductile behavior. We are not focusing on those strain distributions. We are focusing on this strain distribution. So we just need to find the moment capacity of these under reinforced sections. The procedure is here. We just need to obtain the forces in the compression zone and tensile zone. So it's a beam section here. It has a strain distributions. This is the strain in the steel. This is the maximum strain in concrete. This one is the equivalent stress obtained in the concrete. This is a neutral axis. Alpha to Fc is the stress in the concrete at 0.03 strain. This is the depth of the equivalent stress, and these are the stress in the tensile stress in the steels, and these are the compressive stress in the concrete. Please note, we ignore the concrete in tension zone. Now if I convert this whole stress into the single force, concentric force, we can have at the center of this stress, which is half of lambda dn, and this tensile force in the reinforcement. The distance between these two forces is known as lever arm, and that is denoted by z. And if you like to calculate the moment is the couple, like this, force times perpendicular distance, that is force times perpendicular distance, and the lever arm z can be calculated by d minus this value half dn gamma. If you like to calculate the force, it's just generally stress time area. So if you like to calculate the compression force, stress is alpha to Fc, that is the stress in the concrete, times the area, which is the gamma dn depth, times this width b. Let me put this width b here. And similarly for tensile force, the area is AST. So the total area of the tensile reinforcement is AST here, times the yield strength FSY. Now this section is in the equilibrium, so we can maintain the horizontal equilibrium by saying the sum of the force in the x direction equal to 0. This one, let's take this one positive c, and this is negative t equal to 0. Now we substitute this value. C is alpha to Fc b gamma dn, that we substitute here, minus we substitute tensile force here equal to 0. If you expand this one, it's become this equation equal to, we bring this one across, then become plus AST AF1, and then if you have dn, we can bring all this parameter down here, alpha 2 gamma Fc dash and b. So we have an equation to calculate the dn, depth of the neutral axis, and that is dn. Now we just need to know what is the length of the lever arm, because to calculate the moments we just need to know the lever arm length. So what is the length of lever arm? So the lever arm can be calculated by d minus these portions. You can see this is whole thing d, take away this half dn gamma will give us this z. So that is d minus half dn gamma, that is just coming from here, d, which is d minus half dn gamma. That has d, I just put half as a 0.5 dn gamma, d minus 0.5 dn gamma. I multiply d and divide by d because it becomes 1, so it's exactly the same, but I just multiply by d and divide by d. Bring d as a common, d 1 minus, take the d out, and we are left with this d. Now in that case, d 1 minus, now we substitute dn, we have 0.5 gamma d. Now we like to substitute these equations, dn equal to 1 alpha 2 gamma a fsy Fc dash ast b. So that's we substitute here, that we just obtained in the previous step. So that's dn we substitute here. So we have 0.5 gamma dn, gamma and gamma will be cancelled, so that is gamma is not coming into picture. So 0.5 dn on d, so 0.5 dn we substituting by this one, and there is a d here, and alpha 2 gamma is removed, ast fsy ast b, and that is the d. Now the moment mu of the couple is therefore, so this is the moment mu, t times z, as you can see here, t times z, moment equal to force times perpendicular distance. So we substitute tensile force, which is ast times afy, so we substitute this ast afy and this z value d, and whole equation. So this is the equation to calculate the moment capacity of under reinforced section. Now a couple of notes based on these equations, that then all the details concerning the cross sections are known. For examples, if we know all this ast fsy d alpha 2, we can get it from standard fsy fcs ast bd, it's all given except this value mu. Then we can calculate ultimate step capacity mu. Then this process is known as analysis of the, because when we calculate the moment, this is the analysis process. But if we know, if we require capacity is known, if you do the bending moment diagram and if you find it out the applied moment, then it's known. Then the area of tensile reinforcement ast may be found by solving this quadratic equation. So if I say that if I know this value, I can find this ast, all other parameters known, then we need to find the tensile reinforcement area, and this process is called design of the reinforcement. Some notes, that this equation may be used whenever the width of the compression block B is constant, down is depth gamma d. And what does it means? That this width B, so this cross section should be constant. It should not have like a T sections or kind of L sections, or where you have a different cross sections. So this equation generally applied only for the constant, as may happen in the case with T and L sections. The shape of the concrete in tensile zone does not matter, as its strength have been ignored. So it's just a quick video on the calculation of moment capacity of the under reinforced beam section. Thank you.